Koon Tong Goh from Center for Quantum Technology Singapore, and he's going to talk about device-independent quantum key distribution with the random basis.
Hi, can everyone hear me?
Yes, I can hear you.
Very nice. Good afternoon to everyone. Thanks. I would like to thank the organizers for organizing this amazing conference and the opportunity to speak to everyone about our recent result on the device-independent quantum key distribution with random basis. I'm Koon Tong, and I'm from the Faculty of Engineering of the National University of Singapore. And I would like to first introduce a little bit about the whole motivation of this work, the entire field of quantum key distribution, or QKD. So the problem that QKD would like to solve is this key exchange problem. And this key exchange problem usually involves two parties, Alice and Bob. And Alice and Bob are both, maybe I'll use a pointer. Alice and Bob are residing in this secure zone where Eve, the eavesdropper, could not access to. So the goal of this key exchange problem is such that Alice and Bob would both obtain identical and secure keys. But in order to do so, they have to communicate through the unsecure channel that is outside of the secure zone. So what Alice would do is that she would duplicate the key and she will encrypt the key and send it to Bob. So once the key is in the unsecure zone, you know, Eve could do anything to the encrypted key. So if the encryption is not strong enough, Eve could always duplicate the key and encrypt it again, make a copy, send it to Bob, where Bob will decrypt the key. And in this scenario, it's not very nice because now Eve has the same key as Alice and Bob. So if Alice and Bob were to use the key to encrypt sensitive information, Eve has full access to that information. So the goal of quantum key distribution is to solve this problem. So we know that the channel is unsecure. So there has to be a strong way of encrypting this information. So in this case, what Alice would do is to take the key, feed into the quantum state source to produce a quantum state depending on what the key is, and send it into the unsecure area. So in this case, Eve would want to try to read information from the quantum state, but she cannot do so without disturbing the quantum state. So if she doesn't want to disturb the quantum state, she will not get any information from the quantum state. She has no choice but to send it to Bob, where Bob measures the quantum state and obtain the identical key. In this case, Eve would not be able to gain any information about the key, and the key can be used to encrypt secret messages. So that is the main motivation of quantum key distribution. So it might sound like quantum key distribution is, you know, the end solution for this problem, but you know, even this powerful tool has its vulnerability. So perhaps let me explain the ideal protocol, the first quantum key distribution protocol, the BB84 protocol, where you have a quantum source. Alice has a quantum source. The quantum source would produce one of the eigenstates of the Z and X Paulis, and the source would send the signals to Bob, who will measure either in the Z or X basis. That would give perfect security. If the error rate, the quantum bit error rate is 0, but of course, if the quantum bit error rate is non-zero, then you know you could still get some security, but everything is fine. You know, everything is watertight. However, in a realistic BB84 protocol where you have realistic devices, you cannot say that you have a perfect. It produces a perfect eigenstate of Z and X basis. So you know we kind of not know what the state is. Maybe we have some good estimation. That would so that kind of miscalibration and poor characterization of the source and the measurement would result in an underestimation of the quantum bit error rate. And by underestimating the Q bar, what could happen is that you might overestimate the security. So if you have a wrong impression of what the security of the protocol that you have performed might be, then your post-processing, the error correction, and the privacy amplification might produce key that might leak some information to Eve. So that might spell disaster, of course. The other problem, it has to do with the side channels. So sometimes when we implement the quantum state source, there could be some components or optical components in the source that might inevitably leak out some classical information about the key that is used to encode the quantum information. So in this kind of side channels, the adversary Eve could learn something about the key, which would break the protocol as well. So, this might sound like the end for QKD. However, as the title of my talk suggests, DI-QKD will offer some partial solution to this problem. So before we dive right into DI-QKD, let me talk about some ideas that has been introduced that preludes to DI-QKD itself. So in the early 1990s, Arthur Eckert actually came up with this idea of doing QKD that is based on Bell's theorem. So in his idea, one could perform a Bell test. A Bell test is an experiment where you have Alice and Bob having some measurement device, and this device are fed some entangled states. And the rule of this Bell experiment is that these two parties are not supposed to communicate. And what they have to do is that they have to fit in some inputs, X and Y, respectively, into the devices, and that would select the measurement choice of the measurement that will be made on the entangled states. And this device would then output a bit of information, A or B. And by looking at the input-output correlations, we could determine if that the input-output correlation violates a Bell inequality. So an example of a Bell inequality is like the expression below here. This is also known as a CSSH inequality. So if a Bell inequality is violated by the input-output correlations, then we would know that the outputs cannot be produced by a process that is compatible with local hidden variable theory. And what that means is that then Eve cannot perfectly guess the output of the device, since this by looking at the information that's available to her, she could not predict the output perfectly, which means that there is secrecy and QKD can be implemented using this idea. So a few years later, Dominic Myers and Andrew Yao came up with this idea of doing QKD with imperfect apparatus. So this is the first time that this black box treatment of QKD devices is introduced. So what this black box device this kind of black box device framework is all about is that the source and the measurement device are treated as a black box where you do not know the inner workings of these devices. So what you know is that the source is producing some quantum signal that sends to a measurement device, or you can have an entanglement-based QKD protocol where you have a quantum source that is sending parts of the entangled states into the measurement device, but you do not know what the state is. You do not know what the measurement is performed on the states as well. So what their result tells us is that by observing certain quantum correlations from this black box device, we do know something about the measured quantum state and the measurement, but up to some local isometry. That is important because like how the quantum state and the quantum measurement if you were to apply a unitary on both of them, it will give you the exact same correlations. So there is some freedom there, but the most important information about the entanglement, about the measurement is preserved. So in some cases, some of this quantum correlation could even pinpoint uniquely to the state and the measurement. And this will allow the users to perform QKD that this black box device that's capable of self-checking or self-testing, and we know that self-testing has like branched out into a separate field on its own. What happened is that a few years later, inspired by these two ideas by Arthur Eckert, Dominic Myers, and Andrew Yao, Arsene et al. Actually came up with and coined the term device-independent QKD in 2007. In that work, what they do is that they have this same black box framework where you have measurement device that you do not know what are the measurements that are being made, and you have they're being fed with a quantum source that sends some entangled state into this measurement device, and this measurement device will perform a Bell test. So what this scheme does is that we have two boxes, Alice and Bob. Alice would feed a bit of information to select the measurement that to be made on the quantum state, while Bob would now feed a treat because we introduce one more measurement setting, and then they would collect the output. So what this scheme is all about is that the 0 and 1 measurement over here and the 0 and 1 measurement over here would be used to estimate the CSSH violation or the Bell's violation. So if there's Bell violation, then we know that the measurement involved would have some secrecy against Eve. In this case, we use the measurement 0 on Alice to generate a key. On the other hand, on box devices, because we know that the 0 measurement and 1 measurement will not fully correlate with the 0 measurement of Alice, we have to introduce a third measurement that generates the key on Bob's device. The reason being is that you want to select a measurement that would have a high correlation with this key generating measurement on the Alice box. So in this case, there are two components to this protocol. First, we would like to observe a good CSSH violation. Second, we would like to have a low Q-bar between Alice's 0 measurement and Bob's measurement 2. In that case, a low Q-bar and a high CSSH violation would give us secrecy. And I think one of the most important and the biggest leap of this work as compared to other previous work is that the secret key rate can be determined with the Q-bar and the CSSH inequality, which means that we are able to quantify the amount of secrecy that comes out from this DIQKD protocol. So the strength and limitation of DIQKD protocol, of course, this DIQKD has been formulated to be the ultimate QKD protocol. However, there is still some limitations. So firstly, the strength is that the first strength is that the source, the quantum state source can be uncharacterized, untrusted, and even manufactured and controlled by the adversary. It means that Eve could even control the source and what the source does. Secondly, the security of this DIQKD does not depend on the calibration of the measurement. So even if your measurements are miscalibrated, as long as you see a high CSSH violation and a low Q-bar, you could certify secrecy. However, the measurement device cannot be controlled by the adversary. As you can imagine, if the adversary were to plant a radio, like a radio device in the measurement boxes and broadcasting the measurement output, then this DIQKD protocol will be compromised as well. So that is something we have to take note, that we can't allow the adversary to build and control our measurement device in DIQKD. And the next point I would like to point out is that this DIQKD is extremely technically challenging, and it requires a loophole-free Bell test with sufficient Bell violation. And we know how difficult it is to perform a loophole-free Bell test. It has only been done in 2015, and currently not more than 10 publications on experimental loophole-free Bell test has been published. So it's definitely challenging. So as I've mentioned, loophole-free Bell test is one of, like, the stringent requirement of loophole-free Bell test is one of the biggest obstacle to implementing DIQKD, because it requires high quantum state fidelity, So it means that the preparation noise and the environmental noise has to be kept low. And this is challenging because for QKD, the Alice and Bob have to be far apart for it to make sense, right? Because if Alice and Bob are in the same lab, then, well, Alice could just pass Bob a thumb drive of that's filled with the keys. That's more efficient, right? So secondly, the detector efficiency has also to be high, because the reason being is that for loophole-free bell test, you cannot make measurement this post-selection. If you do a post-selection, you might introduce the detection loophole, which might jeopardize the entire experiment. And lastly, we need high repetition rate of a device in order to circumvent penalties from finite size effects, because our DIQKD device doesn't run for infinitely long period of time, so that you have to account for noise and fluctuation due to statistics associated with finite size effects. So the less data you have, the higher the penalty will be incurred to your key rate computation. So that is pretty important, because for photonic system, they usually generate entanglement using SPDC processes. And if you keep the pump power low, then you have a lot of vacuum noise. If you bump up the pump power, then you get noise from the multi-photon contribution. But if you to use a system like coatoms or NV centers, and you entangle them with the photons by doing entanglement swapping, then that kind of system is extremely slow, and you incur this finite size effect penalties. So it seems like nature is conspiring against us to perform a DIQKD experiment, but you know, we never yield to nature, and we try to make attempts to make DIQKD practical, and we go back to the drawing board. So in 2020 and 2021, very recent results, there are multiple attempts to make DIQKD practical. So these works are produced from the research group of Nicolas Sangoa, and as well as Antonio Asin and Stefano Pironio. And what they come up with is to perform the same experiment, but with some modification. So the first modification is known as the noise pre-processing method. So in this case, what Alice does is that when she measures the key generating measurement and get the raw key, she adds noise to the key. And that's what we get here, the A prime. So what they have found is that by doing that in a high noise regime, Bob would have a better chance, or rather have a better ability to guess what A prime is as compared to Eve, rendering them some advantage there. And secondly, instead of using the usual CH-SH inequality to quantify security, there are other Bell inequality that we can use. Of course, in their work, what they do is that they use this asymmetric CSSH inequality by adding alpha to two of the correlators. And in those cases, you can think of this asymmetric CSSH inequality as a family of Bell inequality that in a way generalize CSSH inequality. So for instance, if you set alpha to 1, you recover CSSH inequality. Oh, sorry, I think this local bound is wrong. This only works when alpha equals to 1. So there's a typo here. So I apologize for that. But in any case, this is what the Bell expression look like with two alphas as a prefactor. And it's not surprising that it will give advantage for some of the correlations, because the correlations that maximally violates this asymmetric CSSH inequality will not be the same correlation that maximally violate the CSSH inequality. So by restricting yourself to just one inequality, it's suboptimal. So in a way, once you have a correlation, it's good to optimize which Bell inequality to use to quantify your security. So these two are a very good work that tries to make the IQKD practical. So in the same year, this year, we has also come up with a framework to do DIQKD differently, to make DIQKD practical. So in our work, what we do is that instead of drawing the key from just the A0 measurement, we also draw key from the A1 measurement. So in this case, we have to put an additional measurement choice on Bob's device again, because now we need another measurement that has good correlations with the A1 measurement. So why would this work better? You might ask, by just generating key from the other measurement, which is already there all along since DIQKD was introduced. The reason why is that if you were to generate key from both measurement, then Eve would have to perform measurement on the purification of the measured state in a way that she has to guess what could happen, what would be the likely output if Alice were to measure in this measurement and in the other measurement. And in the ideal case, these two measurements are anti-commuting. So that makes her job even harder. So in our case, we also base our security on the CSSH inequality. And now we have an additional cuber. So because now we have not just A0, we also have A1 that generates the key. So in that case, we have to find the error between A0 and B2 and A1 and B3 as well. So the result of our work shows that there is an improvement of the key rate. So the result is presented in this graph on the right. The y-axis is the cuber and the x-axis is the CSSH violation. So you can see that the good region is at the bottom left, bottom right corners over here. So how do you interpret this result? On the white region over here is where there is no secrecy, or the secret key rate is 0. So on the right, where it's colored, there is some secrecy that you could generate from the DIQKD system. And this dashed line indicates the boundary for the DIQKD protocol with just one measurement basis, one key, the original DIQKD protocol. So over here, we have some experimental points. The dark purple points are the loophole-free bell test results, where the light purple point are bell tests, but they do not close certain loopholes. So when you look at the cluster here, they have low bell violation, and not surprisingly, they are the photonics experiment, and we know that photonics experiment doesn't generate very high CSSH violation. On the other hand, point number 7 is the Delft experiment, where they use NV centers, and the point number 8 is the Munich experiment, where they use the co-atom. And of course, for both cases, they use photons to entangle them, and using entanglement swapping techniques, they could perform a loophole-free bell test. And only these two experiments could exhibit asymptotic positive key rate using our method. But as you can see, if without using two bases and just using one basis, only the Delft experiment could land on the positive key region. And for the Munich experiment, it is out of the positive key region. So sort of we allow more experiment to be in the positive key region. And not just that, if you look at the Delft experiment, the error bars are huge because they have less data points. So in that case, if you look at half of the error region, they actually land out of the positive key region for the original protocol. But using our protocol, our framework, we actually covered most of the error region. But this might make the result doesn't seem very significant, but I think the most significant part is if you look at the finite key analysis. So if you look at the finite key analysis, the Delft experiment would require 10 to the power of 15 runs in order to obtain secret key. And that is by using just one basis, the original DIQKD protocol. And by using our scheme, it has a 7 orders of magnitude improvement. So the number reduced to around 10 to the power of 8 runs, as you can see here. So at about 10 to the power of 8 rounds, this is a log plot, so the 8 indicates 10 to the power of 8 runs of the protocol would allow you to get some secret key rate. So this is still a large number because, as I've mentioned before, these systems are extremely slow. So it can go about 10 to the power 3 runs per day, which means that you can only get positive key in 300 years, less than 300 years actually, about 270 something years, but that is too long. We are not going to wait for that. But we have to note that these experimental figures are about half a decade ago, and things have changed, things have improved. And if you look at the previous plot, by just moving the zero asymptotic key rate from this position to this position, this small change would give you a 7 orders of magnitude improvement. Improvement in the experimental setup could also give us improvement in terms of the requirement of the number of runs to obtain positive key rate. So it is not hard to imagine that if we were to obtain a 2 to 3 orders of magnitude improvement reduction on the number of runs required, then we are looking at the orders of months in order to get positive key rate. And that would allow us to perform a proof of principle DIQKD experiment. So let me go through some of the benefits of using this, our DIQKD framework. So firstly, our framework can be applied to any DIQKD protocol. So recall when our colleagues from other research group that came out with this noisy pre-processing techniques and to use other Bell inequality to certify security in the DIQKD protocol, we can also incorporate those techniques into our framework, because all you need to do is to use the other measurement to generate keys. And it is really very easy to implement because it only requires 1 additional measurement settings on Bob's device. And of course, by adopting our framework, it can only give you a better security performance, or at worst equal performance as the original protocol that you apply this framework to. So it might seem really obvious, but I really want people to adopt this framework, so I still have to advertise. Yep, so to conclude, I would say that DIQKD is a desirable quantum communications application, and right now it is not naive and is not preposterous to think that the experimental DIQKD can be realized in the near future. However, I must note that the commercialization of DIQKD still requires a lot of effort. So in the near future, we are thinking of applying this framework on other DIQKD protocols using some new security proof techniques. And hopefully, we are actually talking to some experimental group, and we hope maybe more experimental group will be interested in doing this experiment so that we can perform a proof of principle experiment of DIQKD. And with that, I would like to acknowledge the team. So this is my collaborators in this work, Rene, who was with us, and now he has left for his other postdoc stint in Ziegen. Ignatius Widom is still with us at the Center of Quantum Technology at Singapore. Ernest as well in Zurich. Ramona has graduated from Hanover, and she's currently now doing her postdoc in Zurich. And of course, Valerio Scarani, who is my PhD supervisor at CQT, and my current supervisor, Charles Lin. So I would like to thank everyone for your attention, and I hope that we can have we can.
Okay, so thank you very much for your very interesting talk. So there's one question from the chatting window, so I will read it. Could you share some idea how to collaborate with Singapore commercial telecom companies to realize the DIQKD?
Oh, okay. So, sorry. Can anyone still see my screen, or my screen is wrong?
You can check this question again using the chatting window. You can click the chatting. So the question is about how you can collaborate Singapore commercial telecom company if we want to realize the DIQKD.
Okay. So I think in Singapore, so there have been collaboration between the university and the telecom company like Singtel. So in that collaboration, most of their work is to characterize the existing optical fiber to see whether or not it is suitable to perform QKD, right? So those are the usual QKD, and it's not the DI QKD version. So the conclusion, our findings is that we can use the existing fiber to perform QKD, but there is currently no study to show whether or not we can do DI QKD with the same fiber. So as you know, the requirement for DI QKD is higher than the usual QKD because of how sensitive it is to the noise and the detector efficiency. So it might take more effort in order to implement DI QKD with the telecom company in Singapore, actually. And of course, the detector that we have to use for DI QKD would most likely be the type of the SNSPD instead of the usual APD, just because the requirement on the detector efficiency is much more stringent.
Okay, thank you very much.
Yeah.
Yes. Okay. So we are already behind the schedule, so we have to move to the next one. So thanks our speaker once again.